to integrate this definite integral, you should hopefully notice it's a u substitution. And u would be your bottom. Now, it's kind of hard sometimes to notice that one because when you integrate that or derive that, it seems kind of dumb. It didn't change anything. Like I didn't get rid of the top. But since I now have the bottom as u, that actually helps, see in a sec why. Because if I go and rewrite this right here, I'm going to rewrite this one as x equals minus the 1 over u minus 1. So I'm rewriting this, and with that, all that put together, you'll end up with the integral. Okay. Now, for this, we also need to change the interval. Let's not change. I'm not going to put the interval there yet, but watch. The top x is u minus 1, minus 1. The bottom is u. Dx is du. So again, I replaced x with this, left the minus 1, replaced the bottom with u, replaced the dx with du. My interval, I'm actually going to switch my interval to in terms of u. So what I do is I go up here, change my interval. So if it's x plus 1, this is going to be 1 plus 1, which is 2. And I'm going to plug in 0. 0 plus 1 equals 1. So I'm going to change this from 1 to 2. Again, I took this u and changed the interval in terms of u. From there, I had the integral from 1 to 2. This becomes u minus 2 over u du. Now, why did I do all that? Now you can divide both of these by u. So if you're doing a u substitution and you can spot getting the bottom to be a u by itself and then possibly manipulating the top by plugging x back into it, you will probably be able to do the integral. And that's the key. Is, again, when you get the bottom to be u, if you can then change this to be x equals, that it's going to be integrable. So this becomes 1 minus 2 over u du. That's the key. If you get one thing on the bottom, you can divide both by u, thus it's integrable. That becomes the derivative. The integral of 1 is u. The integral of this is ln, 2 ln absolute value u. And my intervals from 1 to 2. So u is 2 minus 2 ln 2 minus 1 minus 2 ln 1. I drop the absolute values because they're positive numbers I'm plugging in. And from there, this, if you take that up, becomes ln 4, because 2 brings up, makes 2 squared. So it's a negative. What's ln 1? Isn't that 0? So this disappears. 2 minus 1 is what? 2 minus 1 is 1. So there's my answer. All right, the next one. To do 70 here, I want to integrate this, definite integral. So again, find a u, and I spot my bottom as a good u, because when I derive my bottom, I actually am going to get my top. du is going to be negative sine x, because the derivative of 1 is 0, dx. So now I have this, which I'm going to have on top, I have negative 1, because sine x, I have negative 1, and the bottom is going to be u du. I'm going to leave the interval off for a second, just for a second, because when I integrate this, what do you get? You get negative ln u. Okay. Then from there, you get negative ln. This one I'm actually going to plug in 1 plus cosine x, and the interval is from pi over 4 to 3 pi over 4. Okay. So I kept my interval of x, my interval. Usually I change my interval in terms of u. This one, I plugged it all back in and kept my interval as is. And when I plug all that in, I get negative 1. I could just actually leave the negative 1 out for the end. ln 1 minus cosine 3 pi over 4. 3 pi over 4 is negative square root 2 over 2 minus ln 1. This is a plus, isn't it? That's a plus. 1 plus, and cosine pi over 4, is that positive square root 2 over 2? Now, from there, what you could do, and I'd probably end up doing this, is rewriting this as ln 1 plus the square root of 2 over 2 minus ln 1 minus square root of 2 over 2. Because when I distribute the negative, it flip-flops them, and now I have this. And you can go farther than that as well, but that's good enough for now.